First, thank you for inviting me. The talk has several aspects to it. Part of it is set theory and logic. Part of it is functional analysis. Part of it is optimization. So I'm going to have to sort of get a sense as I'm going what you're more interested in, the different areas that I'll be moving into, because this really doesn't belong to one particular area of mathematics. It sort of spreads itself out, and for good or for bad, meaning the good is that it doesn't get too technical, although there is a very nasty technical side to it, and one thing I could present. But for the most part, it spreads itself even and thin. So we start with a graph. We know what chromatic number is. Yeah. So we could see the vertices of the graph as being a measurable space. So sigma algebra, we'll say beta, which usually I'm going to be thinking of as the Borel sets, the set of Borel sets, and usually with measure, usual Borel measure, and in general, I'm looking at Cantor sets. Okay, so we can do the slight variation and say we're looking at the chromatic number. So this is the number needed to properly color the minimal number needed to properly color the color classes all in our system, in the Borel sets, or in any sigma algebra you want to be. Now, this is a well-known thing because this has been looked at for some 25 years or so. But I just want to show this sort of a basic example of why it could be that this could be larger than that. So we could take V being 0, 1. Okay, the standard Bernoulli shift space. This is the standard shift. And we could say that X, Y is edge if and only if Tx is equal to Y or the opposite, Ty is equal to X, right? And then we'd say, suppose we could say that we can partition the space, of course, yeah, with the property that T of A is equal to B and T of B is equal to A, for example. But what does this mean in particular? It means that T squared of A is equal to A and T squared of B is equal to B. And I'm just making this almost everywhere. It's just an almost everywhere statement. I won't say it's true everywhere because there's some pathological problems here, occasional points where things just get repeated endlessly. But now the main thing is that if you look at this and you realize that T is strongly mixing, so T squared is strongly mixing, and therefore it's also ergodic, we come out of this with the fact that, well, the measure of A can really only be 0 or 1. And the measure of B can only be 0 and 1. But they have to be the same measure, right? So this is strictly impossible. On the other hand, if we want to extend, so if we want to look at mu extends M, the usual Borel measure, and mu is finitely additive, of course, then we can get away with it. Then we can say that there exists such a mu where mu of A is equal to mu of B is equal to 1/2, because we know that T is an amenable action, and we can define a finally additive measure on all the subsets, and whatever subset, whatever measure it's supposed to get, the fact that A goes back to B and B goes back to A, and it covers everything. This has to be true. So we do get away with having chromatic number 2 if we can go to finally additive extensions. Yeah. Yeah.
It's not going to be invariant under T, right?
Well, it would be invariant under T. Yeah. Yeah, pretty sure.
Okay,
because
you can get that.
Hmm?
You still can get the invariant.
I think so, yeah.
Okay.
Yeah, I'm pretty sure you. Yeah, because T is not a barrier to defining all. As soon as you go to more than one T, yes, then there's a problem. As soon as you go to non-amenable action, that is exactly what I'm going to do. Yeah. So the natural thing to do is to look at what happens in non-amenable action. Okay. So can we get, is there exists a graph? Does there exist a graph? Right? For the edges defined by T1, T2, up to TK. That's the point. I'm not using a single T, I'm using a variety of T. And then you're absolutely right. There's no, that's the whole different thing. This is finally additive, right? And it's extending M, right? So we want to at least say, well, it still agrees with M, but more to the point that it says that these things are still measure preserving, right? And T1 to TK still measure preserving, right? And then is it possible that we could have this? Okay. Is it possible we could have a difference?
By graph edges defined by a foundation.
Yeah, sure.
Is this one of them?
That's a good point. I agree with you. And the way I'm going to be using it, it will be defined, the edge will be defined by some of them. So if you take a look at the space, right, there'll be a Borel set over here. Well, it could be simple like that, but let's say we can partition this into Borel sets, so it doesn't look like that, but it's mixed up. And there's a subset of these things that defines the edges. So you can say that a point here is edged over to here if there's a Tj over here, and the set of Tj for which this works is dependent on the location. So for different locations, but the locations are also Borel sets. So depending on where you are, we would have an edge. So it isn't that every one of these things, well, we could have it like that, every single one.
All right, but okay, so there are many ways you can find the edges.
Yes, there's many ways you can define the edges. But what we do demand is that the edges are defined by measure preserving transformations. Which edge is determined by where you are in the set, where you are in the set of vertices. But then the critical thing is where you are is a Borel set. The determination of which edges work as a Borel set, so that the whole system is an equivalence, a Borel equivalence relation. That's what's necessary. But it's a good question because actually the theory that I'm working off of is not exactly like this. I'm not thinking so much in terms of a graph, but rather a rule for coloring a space based on transformations. If we're going to proper coloring, then of course it's a very special kind of rule. And the interesting thing is I can get to that later, there is an interesting distinction as to whether we use the same transformations everywhere to define the edges. If we do, and we're using this concept of coloring rule that I could show you, I didn't plan on putting in the talk, but I can put it in the talk, then it's an open question, right? Now, if you simply say the edges are defined by measure preserving transformations, then the solution I'm going to show you will also solve that as well. And the reason why is because you can go from a Borel equivalence relation to it being defined by measure preserving involutions as a result of Lovash for some years ago. And so the solution that I'm going to show you could be translated over to that as well, where the edges are just defined by a set number of things. But the problem is that they become involutions, and in many places, our point, when you apply Tj to the point, you just get back the point again, in which case you have to say that you get a different point, and that defines an edge. You're not going to define an edge to be a loop when it goes back to itself. So that's a subtlety to it. If we can sort of factor all that out and say at the end what I'm doing is legitimate, then it's fine. But there is a separate question of what happens if the action almost everywhere gives you something else, right? Can you still get this result? And that I don't know. That's an open problem for me anyway. Yeah, maybe when I'm done showing you how this is done, maybe you'll have some insights to there. But at the moment, I don't think it's possible. I don't think you can get this difference if you make that very strong distinction. But let me show you what I do have. Okay, so for a Borel equivalence relation and edges defined by measure preserving transformations, the answer is yes, you can get this difference. Okay, and I'll show you how it's done. So, and I'll also show you the other variations upon it. So I will take x to be minus 1, 1 to the g, and g will be defined by two shifts, and of course it's a free action. This is free. So the free generation of two independent generators. And now for every x, so for every x, we can look at the following. So here's our x, and we can look at what happens when we go T2 of x. We can look what happens when we go T1 of x. We can look at T1 inverse of x and T2 inverse of x like this, okay? And now we're going to restrict our arrows to say that, see, every x can be seen this way. So you have the Cayley graph, and let's say this is a determination. This is the identity, and there's T1, and there's T2, and there's T1 inverse, and so on. And we have in every place a determination of minus 1 or 1, right? So this could be, say, minus 1, and it's 1, and that's minus 1, and so on, right? And then applying T1 is just shifting all these things. So it was at T1 becomes the identity. You just shift everything over, and all the identifications shift with them, right? So that's what we're doing when I talk about, the actions, right? The action of this group on X. And if we look at those actions and look like this, we can say, well, depending on the identity coordinate of X, we could say that the arrows that we're allowed to draw, the arrows that are drawn, are in the positive direction. It's in positive T1 or positive T2. And if, on the other hand, that's minus, then it's in these directions, in the negative directions, okay? So that sets up a graph, a very definite kind of graph, with directed graph with arrows, okay? And from every point, there's one arrow. So from every x, for two arrows. From every x, there's always going to be two arrows, okay? But to every point, there could be a variety of numbers of arrows. So coming into any place, we could have 4 arrows, or we could have 2 arrows, or we could have no arrows, or we could have 1 arrow. All possibilities from 0 to 4 in terms of the number of arrows that can come in, okay? So you can talk about the degree of a point being the number of arrows which come into it, right? Which I call it a passive degree. The active degree is always 2. 2 is always going out, but there's a different number coming in. Now, this is the basic idea that I'll be using. And now, if we want to talk about setting up a graph that we would like to color, I'm going to do the following. Yeah, go ahead.
What is chromatic number for director graphs? I guess the metals.
Oh, I'm not gonna do a chromatic number. No, I'm not gonna do a chromatic number for a director graph. Yeah.
You just with sheet. You didn't say whether it was left or right. It may matter.
The shift.
I mean, which layer is it?
Yeah, you're right. It does matter.
It does.
It does matter which it is. So I usually think of,
But no.
I usually take the positive thing and put it on the identity. So the T shift is where the T2 shift would be, where whatever is here gets placed down into the identity. So that's the usual way I do it. So that, because when you do a semi group, that's the way you do it. Whatever is at the T1 position. Yeah, this is going to be measure preserving, and I'm going to do it for this, and I'm also going to do it for semi group action. Right. Okay, so what I'm going to do, let me put it over here, right, is I'm going to create, from this directed graph, I'm going to create a new graph, okay? And so what I'm going to do is, whenever I have various arrows going into a point, let's call this one X. So whenever I have various arrows going into a point, I'm going to create a click, right? Let's put another one in there just for be dramatic, right? So I'm going to say I have a click here, right? So I'm going to take a new graph that makes this a click, and X goes somewhere else. And maybe it's more modest now that there's two things going to it. And then this becomes a click. Okay. And now what I'm going to do is I would like to color this new graph, which is the click, the graph which is created by the clicks. Okay. But I'm not going to yet color it with a certain number of colors.
So the graph only has the colored edges, not the original.
Yes, that's right. I start with the original graph, which I'm getting from this structure, right? I'm starting with a graph with arrows that comes from this structure. And then I'm going to go ahead and look at where arrows come together, right? And where arrows come together, I'm going to create clicks, okay?
You're saying that X and Y are adjacent. T1 of X is equal to T2 of Y or the other.
Yeah, that you could say that, yeah. It's a kind of it's a double thing. It's so you go in, and then these two are like that are adjacent, right? So they're adjacent that, yeah, that's right. If they both go to the same place, right? And now several things I'm going to do. First of all, I'm going to do list coloring first and go right, later to regular coloring. So I'll go list coloring. I'm going to do list coloring on exactly these points here, that the arrows are coming from, right? And what am I going to do in terms of the list coloring? Well, I'm going to say that the color here on the list, the two colors, are going to be colors associated with this point and associated with this point, right? Now, it's going to be a little more complicated than that for a moment, but the point is, if you think about it, when I say that this is a click and every member of the click has to get a different color, what I'm saying in some sense is that I'm not going to choose, and an arrow is there's two members of the list. It's either going this way or this way, right? To say that I've properly colored means exactly that in every click, I'm not getting two arrows coming in here. It's going to be injective, right? So no member of the click is going to get the same color, and that means the arrows are injective in nature. You never have two arrows going into each other. That's what I'm going to mean by proper coloring. Now, I'll have to explain more about proper coloring here, because so far what I've been doing when I create a list of two, meaning the color associated with the color associated with that, right now, if I say this, I've got an infinite number of colors, which is something obviously I don't want. I want a finite number of colors. Okay, so can I go from an infinite number of colors to finite number of colors? And the answer is definitely yes, because what? Yeah. Yeah.
That's not part.
No. It's the center of the click. It's you could say it's the identity. Yeah. It labels the click. Okay. It labels the clicks come with names, and this is the name of the click. Yeah. But it's not. Yeah, it's not part of the click, right? What's really going on here is like two separate systems, right? There's the system where you give and the system where you take, and they kind of alternate from each other, right? So you could, if you want to, separate them out and see sort of a double system going on. But at the moment, I'm not going to do that. There's a very nice result when you do that, when you separate them out, you realize that you could get a matching system, right? And what you do get is a system of the edges being defined by measure preserving transformations. And one set is definitely bigger than the set. They're both closed sets, and yet you have a matching between the two of them, which shouldn't happen without something paradoxical taking place. But I could talk about that later if you want me to. It's a nice related result to this, right? But that's where we separate out the two halves and look at the half that gives an arrow and the other half that takes an arrow. Okay. So anyway, so I don't want to get an infinite number of colors, right? But what I do need to know is the following. I need to know that when you go here and here, if I could get another color out of this, there's another color, oh, there's a yellow over there, okay? What I definitely need to know is the following, that this thing, this point, and that point are given different colors. Because I want to associate some lists. I want to associate each of these Y's, things that receive arrows, I want to give it different colors. And I want so that they don't have, I want two things. I want a finite number of colors is the one thing. But the other thing, very important, is I want the color classes to be Borel sets. Because I want to make sure that my system is nicely defined as a Borel system. I need a Borel equivalence relation defining this color system, right? So all the places where I color something red, blue, yellow, green, whatever it is, I want to be Borel sets. So the first thing I need to know is that these two things get different colors. And the other thing I need to know is if various members are in the clique and this is going to here, then the one over here that this could go to, something else where this could go to, they also have to get different colors. So I've got the group action that skips over by 2s and the group action which skips over by 4s. I need them to have different colors, okay, in order for the system to work, right? Because I don't want things to be legitimate from the point of no two arrows going together, but actually they're getting the same color, right? Because obviously if two members of the clique get the same color, then they're not being properly colored. So I want to make sure if we're moving away from the clique, that we're not improperly coloring. We're doing okay in terms of the colors. Okay.
Do you have two colorings or one coloring? Because you seem to be talking there is one coloring number.
You're right. I have two colorings. You're absolutely right. There's first of all an initial coloring that identifies a color with this point. That's right. We're doing first the color that, and then once we identify every point with a color, then we can create a list. This X could be colored this color or this color. Yeah? Yeah? We want to define the list that this color is allowed to be colored by coloring this and coloring this, and then these two colors become the list for X. Okay? So what are the things we need for these lists? We need two things to hold. One is that inside of any clique, right? Or I shouldn't say inside of any clique, outside of a clique, if you're going to this clique or you're going to this clique, the clique here and the clique here, right here, this clique here and this clique here, they have to be associated with different colors. The center of their cliques have to be associated with different colors to be able to say X has a real choice. When one color means left, the other color means right, or 1 or 2 or whatever it is. So that's the first thing that we need. And the second thing we need is that if every member of the clique, if they are injected, they don't send arrows smashing into each other, that has to be legitimate from the point of view of proper coloring. And that means exactly that this color and that color have to be different, because we don't want two members of the same clique to be okay in terms of scattering their arrows, but not okay because they're actually, it's not a proper coloring, right? So we need, there's two things about being paradoxical. One is that it has to be non-measurable, but the other thing is it has to exist. There has to be a way of doing it. And if we didn't make this color different from that color, we could create a block from even the existence of a solution. And that's what we don't want. We want a solution, but whatever solution we get should be paradoxical. So the two things are needed. this is that the system is legitimate, that you have different colors corresponding to going one way or the other way, putting your arrow one way or the other way, and the second is that there is a solution which requires that.
Second, so what's the obstacle there?
Well, we want to say,
Clicks.
yeah, we want this, no, the same click. So suppose we have a click, right? And that means you could send it in, right? And you don't want two arrows going into the same click center because that would be, illegitimate, right? That would mean they're colored, two members of the click are colored the same way. But what you also don't want is that two members of the click send their choices away from the click, but guess what? It's not legitimate because they got the same color, right? I mean, if this was red, right over here, and this is over here, blue, right? What we don't want is this also to be blue over here, right? Because this would be, if the solution was, I mean, this should be a legitimate solution for us because we're trying to create arrows which are injective in character. No two arrows go together, right? And so if we could go this way and we could go that way, but this is blue and that's blue, that would not be proper coloring because these are two members of the same click getting the same color. And that's against the rules of proper coloring. But we want to say that's okay if they want to send their arrows up in different directions like this, that's legitimate because the arrows are not hitting each other, right? So we want to allow this situation as being not improper, as being an okay way to do things. And also we want to say that this is not proper. So in order to do that, we have to say this is colored differently than that, as well as this is colored differently from that. Yeah?
So assuming that I am following, which is
Yeah.
big assumption.
Yeah, okay.
So what you want is to set up these colorings, so these not clicks, but these points correspond to them.
Yeah.
So that no matter what you do, you get the coloring, right? So basically,
Yeah.
But there is also a question of selection, right? So you want what else sets.
Yes, that's right.
And that's not obvious.
No, it's not obvious. No, it's not obvious. And this is not.
You have very strong assumptions. On the other hand, it's not clear whether even if you satisfy them, you can do it.
Well,
Right?
I'm counting on Kekris for this
Okay.
and his people that that according to their according to communication with him, as well as looking at articles that he and his school have produced, we can get away with 17 colors. Okay, because we've got only so many choices in terms of these connections, and my count is 16 different things, but the different group elements also are invertible. One is the inverse of the other, so that leaves 8, and it's 2 times 8 plus 1. According to the theory.
Oh, you're very concrete, but you never told us what T1 and T2 were.
Oh no, T1 and T2 it's very clear what T1 and T2 is. So so if you look at all these associations, right? So you look at all these associations. Yes, that's right.
Oh,
Yeah, sure. Just shift it over. All these associations of -1 and 1 just get shifted. Okay? Just like that, yeah. Okay.
So it's the free semi-group, not the free group.
This is the free group.
But if it's the free group, you're always gonna have 4 coming in. It's only the semi-
Oh, yeah, no, but I'm making this special rule here that the arrows are like this. So in half the space, the 2 arrows are going like this, and the other half the space, the arrows are going like this. So that's right. If it didn't,
The sum of 2 semi-
you could, that is not really. I mean, if you look at the arrow flows, they go all over the place. They're not consistently so. I mean, over here, if x to the e is 1, then the arrow is here and the arrow is here. But over here, you could have x to the e equals -1, in which case it goes back like this, right? Or if it was 1, it goes on. It's a complex system, and it's not like it's flowing nicely. It depends on each one of these associations as you go on, whether it flows back or flows on or flows to the side. It's a rather chaotic thing if you look at it. Well, I suppose in some ways it's very orderly, and in other ways it's very chaotic. If you're looking at it in terms of where you are at a certain point, and when you're taking a pathway, is it pluses or minuses going on, then it looks very chaotic. It's random. But from another position, it's not random, right? Looking at a global situation, you're breaking the space down into sections, one which goes one way. So sort of the problem is, that there's really two topologies going on here. There's a topology, which is the Cantor set topology, right? For which you have something like this. You've got halves and quarters and so on. And there's another topology which has to do with what happens here, right? The nearness of the pathways you go in the orbit. And so you're kind of running from one place to another place, right? Something like that. You're doing a dense orbit, and the dense orbit looks very chaotic from its own perspective as to where it's going to land and how it's going to go through the space, right? So from one perspective, it looks very chaotic, and another perspective, it's very orderly, right? So I'm sort of bringing those two aspects together, that in one way it's going to be chaotic, and that's how we're going to develop paradoxical solutions, necessitating paradoxical solutions. But on the other hand, it's very orderly, so the basic structure is going to be a Borel structure.
When you say paradoxical, you just mean a color, you mean one where the
I-
coloring number is different than the.
Yeah, I mean that any way to color this, with 17 colors is going to be paradoxical. It's necessarily paradoxical. Okay, so this is the idea. So you use seven. Wow, worse than Borel, much worse than Borel. You can't even talk about it being, finally additive measurable. So in the same way that I was talking about when you.
I mean, it's the,
Hmm?
you can better.
The Bonnet-Tarski, yes, the Bonnet-Tarski. So yeah, this goes way beyond Borel. Yeah, it's a leap beyond. Yeah, so that's the idea. That's what I was interested in. Is clearly there's a problem with Borel coloring, but can we go way beyond that to something far worse? How far can we take it? And this is about as far, I think, as you can take it. Right? Maybe you could take it further, but I think this is pretty far. And the amazing thing about it is how simple it is that you can get away with this. So first of all, yeah, 17 colors is enough, and the sets where these 17 colors exist are Borel sets. So everything is in Borel equivalence relation territory. And these, of course, are measure-preserving transformations also, because they're just combinations of measure-preserving transformations. So we can break things up into 17 colors. And now the question is, if we could properly color the click system, right, with the 17, not the 17 colors, but the lists that were using 17 colors, okay, why would that be paradoxical? That's sort of the fundamental question. Why would it be paradoxical? Well, when every time you do a proper coloring, you're defining arrows, right? Because if you say that X, you're coloring it red is, say, the color associated with the Y, or blue, the color associated here. When you make that choice, you're creating an arrow, okay? You're saying, well, from X is an arrow. And when you say it's proper, it means everything in the click is not given the same color, meaning they're not going inward. There's no two arrows which are coming together, because if there were two arrows coming together, some member of the click would be getting the same color, right? So when you say it's a proper coloring, you know that the arrows are never going into each other. There's a flow in the space. From every point, you have a direction, and you never get 2 points going to the same point. It's always an injective map which you're defining from the space to itself. It's an injective map using measure-preserving transformations in the flow, okay? But then what's the problem with that? Huh? Yeah? Why? Yeah. But why is it Banach-Tarski? What's the problem? What is the problem of this flow that you've generated? If you assume there is a flow, which is legitimate, and of course you can't construct it, obviously, you say, well, you can show that it exists using the axiom of choice, because all you have to do is take anything over here and scatter the arrows, right? If you scatter the arrows, no two ever comes together. And you can always scatter the arrows, because if you look at the Cayley graph, right? The Cayley graph, There's one way back inward, and there are three ways which go further out. And you're choosing one, you have a choice of one or two ways. So you have only one way inward. So if you have two possible places for the arrows, at least one of them, if not both of them, are going outward. So if you keep sending your arrows outward from every point, you'll never have two arrows running into each other, right? Because you're always going outward. In order for two arrows to run into each other, one has to come back and the other has to go forward. But you're never doing that. You're always going forward. You're always going away. So with the axiom of choice, you know there is a solution for these arrows, right? And that'll be okay in terms of our coloring, as I said, because no clique will have the same, no two members of the clique will have the same color. And because of this, right, that that you don't get accidentally an improper coloring, that you can always, if you make your arrows always go off in different ways so they never come together, you never get improper coloring. So now, why is it that if you have a solution to this kind of system, you must have something paradoxical? Okay, that's the question. And it's a very easy answer to this, and it's really trivial. Okay, it's really, really trivial, right? It comes right here. One of these options is no arrows, right? One of these options that there's no arrow. And how much, well, what does it mean to have no arrow coming at you? It means that if you look at this system right here, right, and forget this, where X is giving it. Let's see where these guys are giving it. So we could send, the choice here could look like this, right? Because here, this could be the positive one, right? The choice here could also look like this, because over here, that could be the positive one, right? The choice over here could look like this, because here, you get the negative one. And likewise, the choice over here look like this, because this is negatively chosen. Okay. Now, these choices are obviously coming at you randomly in the space, right? I mean, the choice of being a 1 or a -1 is 1/2 in every single location, done independently, right? Because that's the nature of the Cantor set and the probability distribution. We'll take the probability distribution so that every location is chosen to be -1 or 1 with 50% and independent of all the other locations, which means that in exactly 1/16 of the space, it's going to look like this, which means that there's no arrows coming in. Well, if you think about that a bit, the world is getting flooded with water. From every location, there's one going out. So the average amount of water coming onto the earth is 1. To every location, there's never 2 arrows coming in, right? Never. Well, with probability, almost everywhere. But in 1/16 of the space, there's no water coming in. So there's much more water going out than coming in. And that's the paradox, because obviously it means that the sets where the flows are taking place in one direction or another, they cannot be in any way measurable, but not Borel measurable in any finely additive measure system. It's the same thing as the Banach-Tarski paradox. You're dealing with a mapping from two sets, and it's an injective mapping, and one set is bigger than the other, and that shouldn't be taking place. And not surprisingly, if you're going to look at the fibers of these maps, you can start manipulating them around and creating all kinds of paradoxical behavior from them, right? Which is, part of what we do as well, but it's, some people think it's the more pedestrian part. This is the more interesting part. Okay, and I said already why it is that there's always a solution, because there's always a way to just scatter the arrows and make them never come to each other. Now, obviously, I haven't done the full hog yet, because I've talked about 17 colors, and I've talked about lists of 2 colors. Well, that's a discrepancy between 2 and 17, right? So you'd like to be able to bridge that difference between 2 and 17. And as it turns out, that's not difficult, right? That's just sort of standard graph theory stuff, right? So let me show you the solution for that. All right. So this is the standard graph theory approach, right? And it won't work for us, but we can sort of modify it slightly to make it work for us. So if we have a graph down here, right? We have X and we have Y and we have Z and we have edges between them, right? However you want to do it. And there are lists. So we're interested in list coloring. So over here we have a list for Y, right? So the list of Y, and it's equal to some set of colors, right? And we have, it's true for every one of these points. There's a list of colors, which are the allowable colors. And so what we're going to do is we're going to take all those colors, all colors, right? And create a big click of all colors, right? We're going to click together just points, right? If we have, well, doesn't matter, 17 colors. We're using a total of 17 colors. All the lists together encompass 17 colors. We're going to take those 17 colors. We're going to click them all together up here, right? And then for every point here, we're going to attach it to everything all but the list. So whatever the list is down here of the colors which are okay, we're going to click this with all the colors up here, which are not in the list, right? So if we're going to be connecting it to something up here, it has to be something in the list, right? Because we want to be proper about it. So now we take that graph, right? We forget about the lists for now. We just look at those connections up here and these connections down here. We ask, what about a proper coloring of that graph? And what we discover is it's the same thing, that we're going to be coloring it according to lists. The same lists, it's just that the lists may be permuted, right? We may have a permutation of the colors, but the same structure will be there. Modulo a permutation of the colors, we're coloring according to the lists. So we have a proper coloring of the graph using the lists. It's equivalent to a proper coloring where we don't have lists, but we've made these associations up here. Now, that's an old trick of graph theorists, and I didn't know it when I first started, thinking about this. Some graph theorist had to show it to me. Now, of course, this is not going to work for us as is. Why is it not working for us? Because we have an infinite graph, right? So we have a finite number of things colored up here, and we have, an infinite number of edges. And we don't want a graph with an infinite number of edges. We want a sparse graph out of this. But it's not that difficult to do. We just have to say that above every point, there's a personal click, right? Personal click of colors done the way I said. You click it to, you attach it to those colors which are not on the list, and then you sort of click these things together, right? With the same rule that you don't put two colors together. You put, you don't put red to red, you put red to blue, you don't put blue to blue. You just, put almost all the edges, just not the edges that have the same color. And now, okay, yeah.
Isn't degree of vertices uniformly bounded by 4 or something?
That's right.
So what
Below.
is
Oh, yeah, but we don't want, when we do this trick where we want to put it to a click of colors up here so that we move from proper list coloring to proper coloring. We drop the lists. We want to get rid of these lists because, lists are too esoteric. You guys maybe have never seen list coloring before, and that's, yeah, you don't want to do it by lists. You want to do it by you want 17 colors in the system, not lists of 2 colors adding up to 17, right? So yeah, you'd rather have the full thing rather than half the thing, right? You don't want to say, oh, this is a result about list coloring, but it's not a result about proper coloring in general, right? With finitely many colors. So you want to bridge the gap from lists to the 17 colors. You want to bring in all 17 colors and say, I can color this point one of 17 colors as long as it works out with all the other points that I'm clicked with or connected to and all that.
So it seems like you had the wrong idea of what list coloring meant.
Yeah.
I thought you just had some set of colors, you're just coloring by subset, so that's why it's the same.
Yeah, you're coloring by subsets. Yeah, that's right.
So one picture just powers,
Oh no, there's a big difference. There's a big difference because if you're doing a list coloring, you could have a a planar graph like this, right? And And instead of there being 4 colors, there could be 7 colors, right? But this only, you're only allowed 1 and 2, and this one, 1, 2, I might have allowed more colors, or 1, 2, and 3, and this one's 4, 5, and 7. Yeah,
Restricted by the list of things.
Oh, actually, that's what you had over there.
yeah, that's right. You're restricted by the list.
So we talked, you just meant you want your graphs to be locally finite.
Yes, you want-
Only finitely many
Yeah,
edges from a single.
that's right, yeah. So the old trick, the problem is that,
But doesn't this fix also have that problem? Because you're gonna
No.
have to connect, or do you only connect to things which are adjacent?
That's right.
Oh.
yeah. Just look at the T1 and T2 and,
If
yeah.
D is adjacent to W, then the.
Yeah. yeah. You just do it for, yeah. And then, then, modulo on the orbit, a permutation of the colors, you're gonna get the same structure again, right? That's the idea there. Okay, so now I've solved it. Now we know that there's 17 colors. There is a graph. To color that with 17 properly means something paradoxical, because every way you color it is going to give you your arrow orientation. You never have 2 arrows going at each other. So you have an injective map, but the injective map misses a big part of the space.
So
Okay.
the 17 coloring over there was a list color.
That's the list coloring.
Okay, so here you converted it.
Yes, I'm converted into, yeah, that's right, right? So, yeah, that's right. So 17 colors isn't too bad. It's not hundreds of colors. It's not, unfortunately, it's not 5 colors, but it's still, relatively small, you could say, in number, okay? Now, okay, so this is great, and we can do this with graphs. Now, there is something going on here that if you look at the system, if you don't think in terms, oh yeah, I did want to say one other thing. This does depend on the edges. You see, the edges are the clicks, and the clicks are determined by which way you can send the arrows, right? By the decisions here. So in some sense, the edges are determined in a Borel way, right? It's a Borel equivalence relationship, but it's not like edges are always determined by these things. They're determined by some of these things. They're determined by doubles of these things, but it depends on where you are in the space. So we'd like to be able to say, well, we just have a bunch of, generators of a group, right? Which define the edges, and we color by that, and we still get something paradoxical. So if you want to take that route, as I was starting to say before, you still have a paradoxical solution. You still have something which proper coloring is paradoxical, except that you have to incorporate the possibility of a loop, that if the group element fixes the point, you have to say the loop is not legitimate. The loop is not an edge. It's only if you go to something else, you have an edge, okay? And then you can say, well, we can drop now this whole thing about the locality, right? That the edges are defined locally in a different way. Although, of course, in a Borel way, it's a Borel equivalence relation, but still differently. If you say that that is not an edge, then you can make that translation and say, well, you just have group elements going from one point to another point from these group elements defines an edge, and we don't care where the location is. It's not selective in terms of the location. So that would be okay. But if you're saying that's not legitimate, I mean, that's a problem. You should never have an edge like that. Then it's an open problem. Then I don't know what the answer is. And I suspect that you can't. I suspect that you can't do something. You can't have a paradoxical structure like this. That's my suspicion, but I have no solid argument about that.
So I'm lost again. So
Okay,
if you have
sure.
a loop, then chromatic number doesn't make sense because.
Exactly. No, so if you say, okay, so if you say loops, we're going to ignore the loops, right?
Yep.
Then we can translate this problem to one where you simply have a group action, and group actions define the edge with the proviso that an edge means not a loop, right? Then we don't have to be specific about what part of the space defines an edge and all that kind of stuff. We can just say, okay, we have a bunch of measure preserving transformations. They define the edges, but when they define this, it's not an edge, yeah? And then we're okay again. We can just take our solution and translate it to something like this, and we're okay. But if you say, no, this is not legitimate, almost everywhere, no loops, then I don't know. That's the open problem.
I still don't understand. what is the problem?
Oh, okay.
What
So,
are the questions? Like,
okay.
I mean,
So what I've created is a system of edges on a graph, which the edges are measure preserving transformations. And depending on in which Borel set you live in, so you have a finite number of Borel sets, depending on which Borel set you live in, that defines the edges of the graph. So there's a bunch of, well, not like this, but there's a bunch of elements in the group, yeah? They're not generators anymore, just a bunch of elements in the group. And edges are defined by those group elements, right? And depending on where you are in the graph, which Borel set you live in, that determines which action defines an edge. And then this is what I have over here is a system where proper coloring must be paradoxical, right? But if you run away from that and say you have a bunch of group actions and independent of where you are in the space, they define the edges, right? So not dependent on which Borel set you live in, but independent of where you live, they all define edges, right? Not just a subset of them defines edges, which is a subset which is dependent on your location, but they all define edges. You also have a paradoxical solution if only you can forbid loops. If you can only say when a loop happens, we'll throw it away. And then again, you have a paradoxical situation.
It's the issue that the places where you have loops is not going to be measurable. Is that-
Oh, no, the places where you have loops will be measurable. That's not the problem. The problem is that we don't want loops. And if we say we're throwing away the loops, they're not edges. Whenever you have a loop, it's not an edge. And you know, that's if that's a legitimate perspective, then we also have a paradoxical solution where you say that the edges are just defined by a set number, because then you're saying, well, whenever it does a loop, we're throwing it away. So essentially, we're not really running away from a real distinction here, because where it does a loop is a certain Borel set, right? So it's a certain Borel subset. So in some sense, we're coming back to the same thing, which is that to define the edges from any point, you're defining it by a subset of measure preserving transformations, a subset which changes depending on where you are in the space, right? So in my way, you're doing it explicitly. You're saying, well, in this Borel set, these are the edges, right? These are the edges. And if you do it with the Lovász transformation, you'll say everything is an edge except for those which define loops. But it comes to the same thing, because the loops are defined on some Borel sets have these loops, others don't have these loops. If you look at any particular, you know, group element, right? So it really comes to the same thing.
So what is the Lovász theorem about these,
Borel equivalence relation can be defined by measure preserving involutions.
evolution?
Yeah, but yeah. So it's a nice thing, and it does give a new perspective on what I'm doing, but it doesn't really change it. I mean, what I'm really interested in is, can you do something paradoxical where you're not dependent on the definition of where the edges are is not dependent on location? And that I don't know. I don't have a real strong, I have the feeling that you can't. That's my own intuition.
I'm still trying to understand the Lovász.
Yeah.
So what is so given an involution,
Yeah.
what is the Borel equivalence relation? Two things being mapped to each other?
Oh, then it would be the things that are different. So the edges would be non-loops, right? So it's a way of taking a Borel equivalence relation and putting it in terms of a group action. So defining a group action which represents the Borel equivalence relation.
It's an orbit equivalence.
Yeah.
Well, but if you carry involution, then orbit is not very interesting.
Yeah, that's what I want.
Say again?
If you carry involution, then orbit equivalence relation is not very exciting.
You're right. No, I agree with you. I agree with you.
So,
So maybe it's not that relevant anyway. Yeah, I mean yeah, you have more. Yes, sir. You have more involutions. Yeah.
It's not just one.
Generally.
No. You have many involutions. Yeah, you start with a group, you end up with a much bigger group. Yeah.
Also, any countable Borel equivalence relation is given by countable many relations.
That's,
Yeah.
so,
But
Well, they don't get you.
Sorry, like Scott Bennett.
Okay.
so, yeah, I'm not, however you do it, if you want to go in that direction, you're still dealing with the problem that the loops are determined, by location, and you're throwing them away. So, doesn't really change essentially what's going on, the problem. Anyway, I don't know the answer if you don't do some trick like this. Okay, but this trick anyway is nice, and give it an answer. For a Borel equivalence relation defined by measure preserving transformations, edges are measure preserving transformations. It's a Borel equivalence relation, and it's paradoxical in terms of its proper coloring. Right? That's what this delivers, and it delivers in a very simple, almost trivial way. So if I can pull you in another direction now, yeah, in a more function analytic direction, if that's okay. Yeah. Or maybe you prefer a matching problem, but let's, okay, my talk. Okay. But let me go in, okay. Let me go in the direction I've planned, which is more in terms of optimization, right? Now, we know when optimization becomes interesting, it's when you can use a mixture of options. When you're how shall I put it? Your toolkit is not go left or go right, but go left with a certain probability, right with a certain probability. Yeah, where you have a convex set of things that you get to decide. You can say that I'm optimizing between going left or going right, and at some point, if left and right are equally good, then I'm going to say I'm going to go left half the time and right half the time, right? And that's what the usual kind of economic optimization is about, is a sort of choosing things with weights rather than probabilistic weights, or weights in general rather than a determination. Because if you go for a determination, of course, you go to game theory, if you must do a move or must do a move, you have to do pure actions. You never have an equilibrium. But of course, by Nash's theorem, if you do mixed strategies, you have equilibria, right? So the obvious, you may not like this. I hate it myself. I'm doing everything I can to demolish the Nash theorem, right? And that's what I'm about to do, is the demolition of the Nash theorem. So, in a certain way. So instead of saying, if here I have an x1 and I get to choose between two options, this goes to my y and then it goes to the z. And over here I have an x2, and whatever this is over here. So let's say I can distribute weight. And I can distribute weight like this, right? So I can distribute weight. And now, the obvious question is, could I come up with a rule for distributing the weight, a rule which is upper semi-continuous convex valued, yeah? Where you say that if I can go this way or go this way, like an optimization thing, I get so much by going this way, I get so much by going that way. And if the two are the same, I could choose either, right? So I'm choosing between this way, there's a certain cost involved with that, and I'm choosing this way, there's a certain cost involved in that. And where the cost is the same, I could split it, right? I could split it into Q and minus 1 minus Q. And the same thing over here, right? And if I had such an optimization problem where I'm choosing which arrow to take based on some optimizing, and if it's equal, I could take any split of the two, right? That's the standard sort of thing in game theory or in economics or anything like that. Is it possible that I could come up with a system where the only solution to this optimization problem is also paradoxical, where the set where you choose one way or the other way, you look at the set of things where the one choice is made and the other choice is made in terms of the flows, right? The numbers that are there, right? The set where you choose this between 1/2 and 1/3 or whatever, and so on and so on. You look at the fibers of any function which satisfies this optimization. Is it going to also create could it be that it's not just can there be a paradoxical decomposition from this, but is it so that every solution makes a paradoxical decomposition, because that's what we got here in terms of the proper coloring. It's not that there is a proper coloring which is paradoxical, that's easy to do. That's just by scattering the arrows, we can do that. But the point is that any solution which is proper coloring is going to be paradoxical, is necessarily paradoxical. It cannot be anything else but, right? Because any proper coloring means no two arrows coming together, and that's going to mean something paradoxical. Okay, so can we do the same thing over here, where we have optimization, where it's not left or right, because this is a left or right thing. We're sending the arrow here, we're sending the arrow here. That's the coloring. The coloring is a discrete coloring. There's 17 colors. But now what if the colors that we're allowed to use are a continuum? We're allowed to use everything between red and blue, right? Or everything between blue and yellow, anything in between, right? And now suddenly we're in a difficult situation, because what are we running smack into when we're doing that? What's the obstacle to our goal of doing the similar sort of construction? It's Brouwer's fixed point theorem or Kaukotanni's fixed point theorem. These are nasty theorems if you're trying to create paradoxes, because they keep coming up with solutions, right? Right? They keep generating solutions as fixed points. So the question is, can we come up with something paradoxical in light of the Brouwer fixed point theorem or the Kaukotanni fixed point theorem?
If I remember correctly, Kaputani is about the union groups, you can figure.
Yes, you're right.
What the problem?
Well, Kaukotanni is about compactness.
Yeah.
Yeah, and that's the problem that we're running into, because we don't have it's about compactness. That's right. That's exactly right. So, okay. So the answer is yes, however, we can come up with solutions. Every solution must be paradoxical, right? But there are two parts to it. One is G is a semigroup. That's one way of going, and the other is G is a group. Now, as it turns out, this is the much tougher way to go, much, much tougher, because the Kaukotanni fixed point theorem really starts working very effectively on this, right? When you start having a system, with arrows, coming in, arrows going out, you start playing with the numbers, and the numbers just keep on, varying, right? You can keep adjusting the numbers all over the place to make things work. The further out you go, the more adjustments you can make. And the Kaukotanni fixed point theorem is very effective at generating solutions, because you know that whenever you have something which is locally finite, if you just make a big, concentric circle around it, it's finite, and you have a solution. If you just sort of approximate things at the edge, you get a solution, and you can take a convergent subsequence of solutions, and you get a solution for that particular orbit. So on any one particular orbit, the Kaukotanni fixed point theorem gives you a solution. The question becomes, can you put the solutions together, right? Right, that's the problem. But the mere fact that Kaukotanni gives you these beautiful solutions is already a problem, because you can imagine very well, it's not only, Borel measurability, it's finally additive measurable for any, finally additive extension. And that's very broad. So you might think, there's some way to compactify the structure that you're dealing with. It's some kind of solution that relates the two. The answer is no, because I can see your eyes are rolling, and you said, but it's not wild to think that there could be people are clever, and they come up with clever solutions, and you might think, I'm clever enough to figure this one out, something is very difficult, but still can be done. The answer is it can't be done. Okay, and you're right, it can't be done. But it's not obvious that it can't be done. Okay, so, but of the two, this is the much more difficult one. And that's exactly because of the Kaukotanni fixed point theorem. The semigroup one is a much easier one. I'll show you the semigroup one first, and then when you're happy with that, I'll say something about the group one. Let me see the time. Okay. So the semigroup one goes something like this. Yeah. Well, when you start working on problems like this, you think, oh, maybe there's some kind of clever approach that, could make this all work. And I'm just talking nonsense from beginning to end, It's It's always a problem. Yeah, absolutely. So the semi-group, I'll call G the semi-group. It's going to be T1, T2 with T1 to the third T2 is equal to T2, T1 to the third. Okay. And these are only, you're only using, positive powers in the identity, right? So these are non-invertible. These are non-invertible. Okay. And I'll make my X a little bit different. I'll make it 0, 1 rather than -1. So it's a bit of a different structure, right? And I'm going to add 3 more points on here, A, B, C. And you'll see why in a second, okay? And my colors, not going to be 17 colors. It's going to be the 2-dimensional simplex colors. Red, blue, yellow, and all the mixes of red, blue, and like what you learned when you were in, primary school. You call it, what do you call it here in Canada? Primary school, what do you call it, elementary school? Like in the United States, we say it's elementary school, right? Okay. Yes, that's right. That's right. That's right. All these things are relatively simple. Okay. So, X, the colors of these two things are going to determine the color of that. Okay. But the fun thing actually is that the color of XA is going to determine the color of T inverse of XB and T inverse of T1, T2 of that. Okay.
Semi-group version.
This is the semi-group. So when I mean that this determines this, it means if you want to know how to color, if you want to know how to color this, you look to the color of this. And if you want to know how to color this, you look to the color of this. That's the way it works.
So what we mean is that T1 of XA determines color of XB.
That's right. So you could do it the other way around, right? Yeah, I know what you're saying. This looks the wrong way around, but I mean that if you want to know how to color this, you look at the color of this. Okay, so I mean the color of this determines the color of this. That's what I mean. So how does it do that? Well, first of all, what is a point in this space, right? So a point in this space looks something like this. So you have, right? So this is the identity. This is T1. This is T2, T1, T1 squared, and so on like that. And this is going to be a 0 or a 1, right? The 0 or 1 determined everywhere. And that's your typical point, right? It's obviously, it's determined by an infinite number of things, right? And what is T1 of X? Well, what I like to do is I like to think of this as a situation where you have an army out in the field, like the Roman army or something like this, and it has a general and he has a lieutenant on the right side and a lieutenant on the left side, and so on all the way down, right? Lieutenant actually means left, right? Literally, yeah. So he has I want to say a left lieutenant and a right lieutenant. I don't know what the right word is for, if the lieutenant is the left one, what do you call the right one?
Called left-handed stuff.
They are left. Okay, I didn't know. Right. So, so to explain this, you have to think that the general gets killed in battle, and then this guy replaces him, right? So everything here just advances up to that location, and everything which is here is forgotten, right? Their information disappears. And the same thing for T2, where you do this and they just advance up and everything else is forgotten.
Locations get very crowded, right?
No, they don't get crowded. So this right here is an infinite tree, just like this was an infinite tree.
I mean, you have two nodes coming into this one.
Yeah, that's right. But this guy, yeah, yeah. 2 are replaced up here. You're absolutely right. There's twins. Yeah, there's twins. So whenever there's a Y down here and a Z down here, there are 2 twins up here that sit above them, right? That's right. Oh, but the main point I want to make is that it's an uncountable number of things over here, right? So if we want to know how we go from an XA to a T1 inverse of XB, right? And there's an uncountable number of them, right? So we want to know how the color here determines the colors up here, right? Meaning that color here looks to the color down here. We just do this. We put an identity matrix, but instead of zeros, we have small quantities, really small quantities, like less than 100th, small things. So these things are less than 100th, right? Between 0 and 100, something like that. And now, if it's clear, 1/2, 1/3, 1/6, it's clear that the optimization lies right here, right? You choose the row which has the largest value. You put in here P1, P2, so this is P1. The coloring is P1, P2, P3. P1, P2, P3 is the coloring down here. And you choose the row. Optimization for this point is to choose the row which gives you the maximal value. So if it's clear that it's imbalanced up here, you know exactly what to do, right? But if it's not clear, if it's very close to 1/3, 1/3, 1/3, then it's dependent on these things as to which one.
Are you talking about Markov processes? Because in
No.
Markov don't have one, so no.
No, I'm not talking about well, it is.
What
It's
is the matrix about? I don't
It-
what's the purpose of it?
the purpose of the matrix is to determine an optimization. So you, as an entity which is here, has to know how should you color yourself, right? Your color is going to be an optimization. You're going to choose the optimal color, okay? And your optimal color, almost all the time, will be one color, not a mixture of colors, but one color, because most of the time, one of these rows is going to be maximal. If you put anything over here and you have slight changes over here, right, then you're going to get maybe, so if this guy is like 1/3, 1/3, 1/3, so it's ambiguous what's the maximum, right? Then if you look up above here, then say the answer will be 1/3 of the time red, 1/3 of the time blue, probably approximately, 1/3 of the time yellow. And probability 0, mixed. So with probability 0, you'll come up with a mixed solution, right? But with probability 1, you're going to go either with 1 or 2 or 3, right? This row will be the best row, or that row will be the best row, or the third one will be the best row. No matter what you put here, with probability 1, you're going to have one row or another row or another row. You're never going to be mixing rows, right? So your optimization problem is, if there's one row which is clearly the best row, you choose it. If there are two rows which are the best, you choose any mixture of those two rows. And if all three rows are equal, then you choose any mixture of the three. But by doing something like this, you see that through having these slight variations, which are dependent on different variations of where you can be right here, right? Because this is like a copy of the whole space, right? You can have these very, very small differences and create them so that with probability 1, optimum will be one of the three. So this is a purity generator. It takes things which are mixed, and with probability 1 turns out things which are pure, which are 1, 2, or 3 being the optimal solution. So what this does when you do this is it takes a probabilistic, how do you best want to put it, a mixed potential solution, and it turns it into a combinatorial problem. Okay, because almost everywhere you get a particular row which is optimal, right? That's the idea behind this. And now instead of talking about mixtures, almost everywhere we won't have mixtures. We'll just have that decision to go with 1, 2, or 3. And now we're talking about the distributions of 1, 2, or 3 in the space. Does that make sense? And then we want to show that those distributions, cannot be measurable. And the places where you choose A, choose B, choose C, 1, 2, or 3 cannot be measurable sets. Okay, in any concept of measurability, including finally additive measures as well. Okay, so that's the idea in terms of what we do here. But now once we do that, once we know how to determine the colors of the B and the C, we want to know how those colors determine the A. Okay, and that's the fun part. So now that we've reduced it to a combinatorial problem, now we can talk about what happens here. You have a color, you want the color XB. You don't know what color it should be, right? But you have a color for XC and you have a color for XB. I always put the C on the left side, right? And the B on the right side. Because this is corresponding to the T1 action, and this is corresponding to T2 action, right? Down below, I should say. It's down below here, the T2 action, and down below here is the T1 action. But I think of it in terms, because I've created everything, I've made everything discrete, I've made everything combinatorial, that once I get rid of the B's and the C's and just see that actually they correspond to the T2 and the T1, then I think of this as T2 and this is T1. Okay, but now I want to know if I got a color here and I got a color here, how should I color here? Okay, well then again, we ask the question, is this 1? Is the identity coordinate 1? And if the identity coordinate is 1, and the colors are 1, 2, 3, modulo 3, and this is colored I, then the answer is color it I plus 1. So just advance the color by 1. Okay. Now, the more interesting rule is suppose we have a 0 here. Okay. Then we're going to look at I plus 1 and J. So we're going to take this color, we're going to add 1 to it. We're going to take the J over here, whatever that's colored over here. Remember, again, almost everywhere they're colored I, J, or K. There's no mixing going on. So if this is equal to 1, 2, 1, 1, 3, 2, 1, or 3, 1, the answer here is the same. I plus 1 is the answer. If it's anything else, otherwise, it's just going to stay I. It's not going to advance at all. Okay? So that's the rule. And the nice thing about this rule is it creates our paradox. Okay. Now, what is this rule based on, by the way? Do you recognize this rule anywhere? Because it's based on something. I'm not that creative. It's based on something which is 110 years old. Right. So what is it based on? Who was the first one who did paradoxes? Hausdorff. It's based on the Hausdorff paradox. Right. Because what's going on here? With the Hausdorff paradox, the way it works is opposite when you have two actions. You know that this is equal to the identity, and otherwise there's no other relations. And you have this system, where going around the triangle is the tau, right? And this is the sigma. Yeah. You have 1, 3, 1, 2, 2, 3, 1, 2, 3, 1, 2, 3, like that. In the Hausdorff paradox that half the space, if this was measurable by any finitely additive measure, where these things are measure preserving, all of these things are measure preserving, you see that the space is paired up, right? It's paired up of opposite things on the two sides of sigma, and half of them are 1, right? On the other hand, the space is paired up by the rotations, and a third of them are 1. So you can't say the things which are labeled 1 are both at the same time 1/2 and 1/3. And the same thing is going on here. So what we're doing, I first put it up here. Yeah, T1 to the third, T2 is equal to T2, T1 to the third. So I'll show you in a second what's going on there. So it looks like this. Your typical point and its relations to other points looks like this. Here's our starting x. We go down by T1. We go down by T1 squared. T1 to the third, and then we come over here to T2, T1 to the third. And we go over here to T2, we go over here to T2, T1, T1 squared, T2, and then this becomes the same thing, because this is T1 to the third T2, and these two are equal, okay? But this is not the same as that, and that is not the same as that. They live in different worlds, okay? Now, we make two assumptions, two cases, right? One case is that almost everywhere, XE being 1 or XE being 0 is no difference. Essentially, there's no difference between these two things, right? And if that's the case, if there's no difference between these two things, we're in the Hausdorff paradox situation, because we're rolling things up, right? But then opposite here, we're going to have, you know, we're going to have, if this is colored by 2, this is colored by 1, right? If this is colored by 3, this is colored by 1, and this is colored by 1, it could be 2 or 3. We're the same problem with the Hausdorff paradox, that we're going to get, you know, we're not going to be able to, we're going to say half the space is colored 1, a third of the space is colored 1. We're going to have the same problem, because we're going to be rolling up, because if this is happening, if there's no difference, then the 1 just means you're progressing. So you're doing, you know, we're doing this modulo 3, but at the same time, the rule is being satisfied that you know, it's, what was it? It's the, there is no difference if it's one of these 3 options, right? Otherwise, there is a difference, right? So if it's always following this rule almost everywhere, then we're getting the same thing as the Hausdorff paradox. So we have to assume with positive probability, there's going to be a difference. There's going to be a difference. And if we make that assumption that there's going to be a difference, then what we're really setting up is a stochastic problem, right? That these things move through stochastically, where there's going to be a certain probability that you're going to advance, a certain probability that you're not going to advance, and so on. And then here's the touch. Whatever distribution we have, so this is a global distribution to the problem, right? Because of invariance, because we say that these are measure-preserving transformations, whatever the distribution is over here has to be everywhere else. So if that's P, then P is going to have to be everywhere. So if you look at, and it's the same distribution everywhere. Now that doesn't completely explain everything, because what we would like to say is that those distributions are independent. Because if those distributions were independent, then we could run a contradiction. And the contradiction is, well, 1, 2, and 3 at this point right here, right? You have a commonality at that point right there. This is the same point. If you look at the probability, so 1 is put in at probability P1, 2 is probability P, and 3 is probability P3. If you do that, and you make the calculations of what the distribution should be here, and what the distribution should be here, distribution here, distribution here, and therefore the distribution here, if you come up with a different distribution, then you know you have a contradiction, right? And you know that it couldn't have been what you said it should be, and the way you said it should be is the assumption of invariance, right? That the distributions shouldn't be changed according to these actions, right? Which you're assuming that they can't change according to these actions. So if you could do that, you'd run a contradiction to this being measure preserving. Finally additive measure to these things. So, and here's a problem. Looking at this the way it is, they're not independent, right? Because you've got a dependence down here. These two things have a common ancestor, and therefore they're not independent, okay? But we get around that. And how do we get around that? We do the following. In the same way that this sends us out into a different world, which is independent, we're going to do the same thing for all these things. So we're going to create 7 points There's one of them, there's two, there's three, there's this one here, and this one and this one. 1, 2, 3, 4, 5, 6, 7. These are 7 points, and what we're going to do is shift them. So we're going to take a t which involves some various combinations of T1 and T2, so that after we do this, these things are all independent of each other. They have no common ancestors with each other. And there's a stochastic process underlying this, because we made the assumption that with positive probability, there's going to be a difference. There's going to be some stochastic process. And I call this, does anybody here believe in astrology? Nobody. It's true. Astrology is true. Yeah.
So the answer, you knew the answer then.
Yeah.
Yes, the answer was yes.
Yes, yes. The answer is yes, if there's enough codependency. So if you, God created the world, he set this part of the universe in motion, he set that part of the universe in motion. If it's all deterministic from God, then there's going to be dependency, right? And so if God is behind everything, if nothing is chance, if there's no chance at all, then he determines these two things which are completely separate. There's no influence between these two universes, right? Or between these two solar systems, but he created them together and they act in concert. So if you can look over and see the other solar system over there and see what it's doing, and let's say whatever it's doing is what's going to happen to you in 5 years' time, then you can predict the future because you can see, oh, this is the way the pattern's going to go. It's been determined by God. We can't do anything about it, right?
But how were the patterns figured out? I mean, assuming that that's correct.
That's another question. That's
a good question.
that's the challenge of an astrologer. That
Oh,
they have to use their minds, and they're scientists, right? That's what they claim, So that's an astrologer's task. Anyway, but the problem is if there's any kind of stochastic process, if there's any kind of non-determination, if there's any kind of chance in the way this develops and that develops, within a few years, it just gets all, whatever God's plan was, it gets all muddled up and it becomes in the limit independent, right? So you can't look over there and make any conclusion from what's going on over there because it's all been mixed up. What you really should look at yourself, how, in order to understand. So that's the point. Because we're assuming there's at least a little bit of stochastic process here, we get independence from all of these things. And once we get independence from all these things, these are also measure preserving. So whatever you say in terms of, what's the distribution of things when you do these, these actions, right? The same distributions that were there when you looked at these things are also the same as here, because all you're doing is a shift, right? And the whole measure, it's a measure preserving operation, this shift. So you're only using a finite number of situations, what's happening here, what's happening there, and so on. So you're getting, again, that these things should be independent of each other. And once you see that they're independent of each other, you can do this little trick. You can determine exactly what this distribution should be, and it's 3 minus the square root of 7, 3 minus the square root of 7, and twice the square root of 7 minus 2, minus 5, so like that, right? When you assume that these are independent and you have the same distribution and on both of these things and you get the distribution here, it's easy. You just run a standard, not Brouwer's fixed point, but the other one, the Banach fixed point, right? Gives you a unique distribution out of this. So you know what this distribution should be. Now you can plug it in. You can say, with this distribution, we have 1 over here. With this distribution, we have 2. And then you take this same thing and you plug it into each of these things. You run it through matrices because you're assuming independence. I use Wolfram alpha, right? And I end up with a grand distribution up here, right? Which is based on the assumption that that was a distribution everywhere else. The grand distribution is very close to this, but it's not equal. Right? It's not equal. And it's not equal because it would be equal if what's here if I could take these 2 points and pull them apart and say they could have different colors, right? And then I looked at all the different color combinations, right? There are 9 of them in all. And I did it. If I made the colors according to this, and I did this calculation, bang, I get exactly this back again. Precisely, because this is the global distribution as determined as a fixed point. The unique fixed point, you know, the Banach fixed point is this. It's a unique fixed point. And if I make the assumption that the colors are distributed in this way according to this, and I roll through here with tons and tons of these calculations by Wolfram alpha, bang, you get exactly the same thing back again. But if you assume that this is the same point, so this is not happening, and that is not happening, there's only 3 possibilities, and I stick them in according to this distribution, I get something different here. And the difference isn't much. It's like 0.000, is it 4, I think is the largest one, right? It's pretty small, but it exists. And no matter how small, it's a contradiction, right? A win is a win no matter how small, right? If you win in overtime with, you know, extra innings in the 13th inning or something like that, you've still won. And that's what it's like. So you get a difference. The difference implies contradiction, and you could not have been an invariant system, right? Yeah, that settles that. That's published, by the way. That's published in Mathematische Annalen last year, okay, with a whole section on the implications for optimization, for game theory, for all this stuff. That you can have equilibria, which are completely non-measurable to the extent that you can't talk about your expected payoff of those equilibria. Expected payoff doesn't exist, right, of your equal. So you can have an expected payoff, you can have an expected value of your optimization, you can optimize. I shouldn't say of optimization. You can make choices and get an expected, you can make choices which are measurable in character and get an expected payoff from it, or you can optimize, but you can't do the 2 together. Okay? It's impossible to bring the 2 together. Okay. Anyway, so that's that. Oh, I'm over. Let me just say a few words, very, very short few words about what happens in group action. Right? With group action, I'm going to do something very similar in nature. Right? I'm going to, but I'm not going to use 2. I'm going to use 5. I'm going to use 5 different choices. But the same idea that there's the positive directions and the negative directions. And if XE is positive, we go in one of these directions. And if XE is negative, we're going to go in this direction. Okay? And then we get exactly the same thing, that we could have up to 10 arrows going in, or we could have absolutely no arrows coming in. Okay? And then what we're going to do in the system, so there's going to be a P here, a Q here, whatever. When the sum is equal to 1 plus 10 to the minus 11th, that's the key point where a point here screams and says, don't send me any more arrows. Don't send me any more weights. I don't want any more of this stuff. So if it's right here, I'll say it's R, and R is between 0 and 1. And if it goes over that, R is equal to 1. If it goes under that, R is equal to 0. And now, if you're right over here, what's the cost of sending something over here? The cost is going to be the probability of sending it times R. Okay, I need to add that little thing in there. So there's a little bit of a finesse here in terms of how you define these things, but it works out fine. It's going to be P times R. And what the important thing there is that if you look at a chain of these values, so if you have here, down here, an R, and you have a P here, but you have a Q1, Q2, and there's going to be 5 of them, right? So there's 4 ones going up here. And now you have an R1 and an R2 and so on. You're going to see that R1, Q1, if you're in equilibrium, R1, Q1 is equal to R times P, right? And that means that the R1 is equal to RP over Q1, sorry. right? Or Ri, you get those equalities, right? Now, what does this mean in terms of how these chains develop over time? You're going to be multiplying by the P's and dividing by the Q's. So if you have something like this and you want to see, right? So you're going to have 4 ways going up. Do it like this. Varying numbers over here like that, right? What you're interested in is a progression of a product of Pi over Qi, where you're going to be talking about, P1, P2, Q1, Q2, and so on like that. You want to see what's going on here. And if necessarily this goes to, well, not that this goes to infinity, but that some branch goes to infinity. If you can argue that some branch going up goes to infinity, some branch, this goes to infinity, then you've won. Because that means that this situation is not sustainable. The situation where there's a positive R being used here eventually breaks down because it can never be infinite. The P times R at most is 1. So if R is positive, and this is going to infinity, eventually you'll break 1, right? Which means that eventually the system falls apart, right? So that means that with probability 1, you don't get any of this R taking place in the system, right? If everything gets equalized, you're doing an optimization problem. And that's exactly the situation where we get the paradox, because that means if the sum of things coming in is no more than 1 plus 10 to the minus 11th, but remember there's 10 to the minus, no, 1 not 10, sorry, 2. But 10 to the minus 10 is the probability of having no arrows coming in at all, because there's 10 places which could send you arrows, but with a half probability, there's always no arrow coming in. So if you can show that is never really happening, you're never going above that, then you've got a paradox, because again, you're defining a flow, which is, not going above this. So you have to take this times, it's going to be 1 plus 2 to the minus 11th, and then you're going to have 2 to the 10th minus 1 over 2 to the 10th, right? And that's going to be less than 1. And again, you're having a flow which equals 1 going out, but you got less than 1 coming in, and that's going to have to be paradoxical, right? So how do you do this? And what you discover is, if you're going to make the argument that there's some pathway that does this, I don't know how to make that argument unless some probability is coming into the picture, right? To say that I have some probability distribution on this flow, right? And according to my probability distribution, the expectation goes to infinity, right? So what I'm really looking at when I'm doing this, and then I take, of course, if I want to do this, I take the logarithm, right? I'm going to be, and I'm doing probabilities. I'm looking at something like this: log of Pi times Pi, summing this up, plus Qi log of 1 over Qi. Okay? And this is I going to infinity. So what is this right here? Yeah. What kind of thing is this? This is entropy, right? Yeah. And this is negative entropy. And how am I doing the changes? Well, I'm doing the changes in a way so that the entropy here gets maximized. How does it go? I should say minimized. The entropy gets minimized when this is equal, right? And the other one is a different situation where we will take a certain distribution here, which will fix, but will vary these things here. And that's the other thing of entropy, which goes the other way. So these two results in entropy, one is that one of them is forgetting it already, but there's two basic theorems in entropy, and those two basic theorems in entropy allow us to compare this with the standard approach, the standard way of determining what these are going to be. And the standard way of doing this is going to be a situation where we we look at each of these things and we look at how many of these arrows are coming in, and we try to work this out so that what's sitting over here is all equal, so that the pain, the cost level is the same here as it is in each of these locations, right? On a single process, right? And that single process is going to be related to the multiple process. And to do this, problem with this is that we have to consider very small gradations of different levels of P. I have to go to gradations of 1 over 20,000. It's going to be a little difficult to explain why it's 1 over 20,000, but it's because of this, actually. It's because of the 1 over 2,000, which is right here, and the 10 different options that you go up when you do this. So I go to gradations of 20,000. So 1 over 20,000, 2 over 20,000, so on. Each one of those things has to be analyzed in terms of the different degrees which are here, right? The different possible for degrees over here is like 400 different possibilities. So I'm already talking about 20,000 times 400. I'm in the millions, right? And I have to make millions of calculations, and I have to consider those calculations of how far up this R goes when I go to the next level. I have to consider those calculations with all the distributions of these different possibilities, right? I mean, what's the probability of it being this sequence? What's the probability of that sequence, and so on? So I'm lost. I'm absolutely lost. It's too much to calculate. I can't see what's really going on anymore, except what do we have today to rush to our help? Computers. So the computer has come up with an answer, that there is a Markov chain where the probability, the degree to which the Markov chain increases, I shouldn't say, yeah, the Markov chain has an expectation. It's a super martingale, and the amount to which, no, sub-martingale, sorry, it's the other way around. The amount to which the sub-martingale increases at each step in expectation is 1 out of 1,000, right? And meaning that this value of R increases, it adds on the value of 1,000 on each step on the average. So sometimes it plunges, sometimes it goes up. And that's enough, because we know that it doesn't matter what that number is as long as it's positive. We know that almost everywhere it eventually will go to infinity. And that's exactly what we want to show, meaning that these chains have to break somewhere. They're not sustainable. Okay. But the only intuition I can give you as to why this is true is the difference between harmonic averages and regular averages. So what happens is that when these numbers are small, when these numbers are small of arrows coming in, this variable goes up. And when they're large, this variable goes down. We want to show that it goes up almost everywhere to infinity, right? As a Markov chain. And as it is, if you look at the averages, it's going to go down. These numbers are going to be too big. If they're exactly 4 coming in, then it's a steady state. And on the average, they're more than 4. They're 4.5. But the effect of being a small number, the effect of being only 2 or 1, is a much larger effect. And that larger effect is the same thing as saying that, well, if we're dealing with 1/5 as the norm, because there's 5 things, this has a much larger effect than 1/8. Because you see, this is a multiple of 2.5, and this is a multiple of something like 1.6 or something like this. So this is a much stronger effect. And that's what's really operating here, that when you see those variations in terms of the degree, the smaller degree variations are much more powerful than the larger degree variations. And that sends on the average these values upward. So most of the time, these values are going down, but every once in a while, they're going more powerfully up. And on the average, they're going up, but by a very small amount, right? And it's such that if you try to solve it, well, I tried to solve this with 4 directions, I couldn't do it. I could not make the argument. No matter how I tried, I could not make the argument. With 5 directions, I could make it. And that's because just at 5 is enough variation to make this thing work. Okay. So I have no simple argument. I have an intuitive argument, and I have a computer which has confirmed it for me. But I have no solid argument that says this is why this thing is happening. But it's happening because I believe the computer, and I believe the computer what it says, right? So I believe it's happening, you know, and that's good enough for me. It's computer-assisted proof. But I would love for a clever person out there to explain why it's happening by coming up with a general theorem that says this phenomena is ubiquitous. It's happening all over the place. It's happening in all kinds of different examples and all kinds of different structures, not just this thing, which is computer, you know, confirmed, right? Which involved months of work and lots of trouble for me. I would like somebody to say, no, come on. This is everywhere. This is the common way that the world works. And it would be great if somebody could do that, because if they could do that, then they could say that there's lots and lots of phenomena out there in the real world that the only solutions are paradoxical in character. And the interesting thing about this whole structure is that the axiom of, usually most people say that Banach-Tarski paradox and related things are irrelevant to the real world, right? Because they need the axiom of choice, and everything in the real world, you don't assume the axiom of choice to do standard mathematics. You don't have to accept the axiom of choice. You can reject it and still do standard mathematics. And the real world works by standard mathematics, doesn't work by the axiom of choice, right? So Banach-Tarski can't possibly be relevant to the real world. But this is what we're doing. We are suppressing the axiom of choice for as long as we can, right? And what we're showing is that there is not a measurable solution, right? There exists no measurable solution to show that we're not using the axiom of choice. What we're using the axiom of choice for is to show that there is a solution. So by suppressing the axiom of choice as long as we can, we're making this mathematics relevant to the real world. And at the last moment, we say, oh, but by the way, in order to have a solution, you do need the axiom of choice. But that's an afterthought. Yeah, that's not the core of what we're doing. Okay, any questions now?